Hello everyone. So let us begin, and we will be studying a little bit about statistics, and we'll be starting our chapters from where we left off in probability. In the meanwhile, we have done a bit of integration and a bit of calculus to add our supplementary skills, and also what we did was we made sure that the probability portion got into multiple random variables and stuff like that. Now our entire goal of this was to study higher probability and statistics, which we shall begin, and for that we need to know the basic to intermediate portions of statistics and how all those probabilistic criteria and solutions would actually work in a real life scenario, right? So I'll just write it down and let us see. So what we are doing is we are beginning a bit of statistics here. So in statistics we deal about something called data. When I say data, what I mean is we have clusters of points which represents some identity or some information about a certain quantity, and we would like to investigate about those data points or those cluster of points, and we would like to find certain information about it. For example, what we can do is we can measure heights of certain people. So let's say we have 10 people, and what we do is we measure heights for each of them. What we can do is we can name the heights measured as x1, x2, and all the way up to x10. Let this be the data points. Okay, so what are these? These are the data for our sample experiment or whatever we're going to do. Now using this data, what we can do is entirely a different subject, because there are a lot of things we can try on this data, but for the basics, for the sake of basic statistics, what we can do is we can find the mean, the mode, the median, we can find the skewness, the kurtosis. Also we can see if they fit into any probability distribution, and moreover what we can do is we can find probabilities of certain heights being improbable or certain heights being like very likely, right? And maybe there are more than 10 people, maybe there are like 1000 people, and we did a random sampling of those 1000 people, and we selected 10 people at random, and then we selected the heights, and from this heights what we need to do is we need to give a general idea about what would happen to the heights of the other people, or you can say the height of the population, which is of the 1000 people. Can we get an idea about the height of the population from the height from the data points secured in this sample? That is the ultimate question. That is, let us say we were trying to investigate some statistics about the whole country, and there are a lot of people in the country, right? So let's say there are 100 crore people right now, for example, and what we want to do, we cannot sample 100 crore people, that would take a lot of time, and that is why we are being realistic here. We are not really being mathematical, because in mathematics we can even sample 10 to the power 100 people, right, with in a finite number of years, but that doesn't make sense. So let us say we can sample 1 lakh people or 100,000 people, and we would like to get an idea about the whole population from the sample of this 100 lakh people, 100,000 people. And what we would like to do is we would like to select them randomly and uniformly from the population, so that no selection is biased, every selection is uniform, and every selection is equally likely. When we do that, the question is, can we get the idea about the whole population? Ideas like what is the average height of the population, ideas like what is the height that goes on the furthest, above which range do we have a 20% chance of getting a certain height, and stuff like that, you know. So we shall begin with something called mean. So what is the mean? Let me write it down. right? Similarly, the median, so if this is the mean, the median is given by and after we are done sorting the data in ascending order, what we need to see is the middle points. Now, since there are an even number of them, there are two middle points, that is x5 and x6, and they contribute to the median m, which is given by the average of this two. Okay, and if it were not the if it not were even, let us say we had 5 quantities, then there is only one middle number, that is the third one, so we only take that one, right? So it makes sense, because what we understand from this kind of criteria is that we need to be clinical about our data set, and there are a lot of things we can do with the data, and it's usually a good idea to sort them into ascending order before doing any calculations, because it helps us figure out how the data is increasing. We can also graph the data. So this mean, this median, whatever we're talking about, these are called statistics. So statistics are basically a function of the data points. So an example of a statistics would be so covariance of x comma y would be e of xy minus e of x into e of y, right? Where e of y is defined as integral over all r y into f of y dy, and e of xy on the other hand is basically a double integral where fxy x comma y is the joint distribution of x and y. So this provides the way to make sure that we have our expectations correct, and obviously integration is very much required in each of probability and statistics courses, because integration and derivative, they form the base of calculus, and in each step we shall find ourselves to be doing some kind of integration or differentiation, right? So that is one way. Now let us see what we can do with some of the things we have here. Let us begin with a topic here. So what is point estimation again? So we have talked about it before in probability, but let us talk about it in detail here. What is point estimation? Suppose we have B, a point estimator, for a parameter theta. Now what we do know is bias of a estimator is as follows. So bias of an estimator is given by expected value of the estimator minus the estimator. You see, so that is how bias is defined, and we call it unbiased if bias is 0. So we call so if this happens, we call our estimator unbiased, right? Now we can take an example to see that why this is the case and how we can prove such questions. So let us take a small example. So that is the question in we need to show, not of itself, obviously it's unbiased estimator of theta equals to exi. The parameter is theta, which is equals to e of xi for every I, right? So how do we show that? We see that e of this phi cap is basically e so now we use the properties of expectation as follows. Therefore, we see that E of phi cap is basically equals to theta, which means it's a phi cap is an unbiased estimator of theta, and that is why it is basically unbiased, and the problem is solved. Now, this is how we solve this problems, and showing that something is an unbiased estimator specifically involves finding the expectation of the point estimator, and this expectation may well involved some kind of integration or summation, which we have discussed before, I think, and those are required. Now After this, what we will learn is the mean squared error. So this is the mean squared error, because phi cap minus theta is the error that we make when we are going to estimate theta based on phi cap. Because see, phi cap is an estimator of theta, right? But since we say estimator, we are not really guaranteed that phi cap would always equal to theta. So it estimates theta, so there can be some error, and that error is given by phi cap minus theta. And mean squared error is basically we square the error first, which is phi cap minus theta squared, and then we take the mean of it. And in statistics and probability, when we say mean, we always mean the expected value, because the parameters and everything else, they can be a continuous random variable or a discrete random variable kind of thing, and we need to do integration or summation over that, right? So that is one way. Also, what we can find out from this is, so the MSC is basically the equal to variance of the estimator plus bias of the estimator squared. This is another way to find out that. Now, here comes an important property of showing something is a consistent estimator. So our topic is how to show how to show if some estimator is consistent, right? To do that, what we can do is we say minus theta is greater than equal to epsilon and this is equals to 0, of course, for all epsilon greater than 0. So this is basically the definition for the epsilon delta case and stuff like that, and we can make sure that this works. So let us do one example for that. Suppose x1 x2 all the way up to xn be a random sample with mean e of xi equals to theta and variance of xi equals to sigma square. Okay, we need to show that is an consistent estimator of theta. And obviously we first do the integral definitions of this. We want to say that this is, since let fxx be the common PDF, then exi is simply fx dx, while variance of xi is x minus exi squared fxx dx. Okay, and we want to show that theta n is a consistent estimator, where theta n is basically equals to the sample mean. So given and we would like to show that this is the consistent estimator of exi, and let exi be equals to theta, which is also given. So therefore we need to show the following. So then probability that theta n cap minus theta absolute value is greater than equal to epsilon is equal to, so what we do see here is that they have a common PDF and they would like to, they can be treated as equals, right? Now this means that what we can do is we can use the Chebyshev's inequality here, because we see that E of theta n cap is E of 1 by n summation of I equals to 1 to n xi, which is 1 by n and this becomes theta, right? Therefore using Chebyshev's inequality we have less than equals to variance of theta n by epsilon square, and now variance of theta n is basically variance of x bar by epsilon square. Now what is variance of x bar? Variance of x bar is simply equal to and this would be 1 by n square variance of summation from I equals to 1 to n xi, and this would be n into sigma square, so it becomes sigma square by n, right? Therefore probability that theta n cap minus theta is greater than equal to epsilon is less than equals to sigma square by n epsilon squared. Therefore, limit n tends to infinity, probability that theta n cap minus theta is greater than equal to epsilon is less than equals to 0, and this means that obviously since probability can always be is always greater than equal to 0 as well, therefore limit zero. So theta n is an estimator of theta, and this is proved. And added with this would be also the required videos, because we needed it here and we would need it in other videos as well, where it would be embedded as well. So you can just watch that if you want to see some parts of it, or you can skip that. The next video we shall again go on to do some other consistent estimator things. Now, functions and continuity were a chapter where we understood how do we actually define continuity for functions of higher dimensions, though that is like functions which go from one Euclidean space to another Euclidean space and stuff. But it is not entirely clear as to how we can understand if f from r to the power n to r to the power m is differentiable, which means that we know that f from r to the power n to r to the power m is differentiable, but we want to understand what is the condition of so, right? So when it was continuous, we understood that for every epsilon greater than 0 there would exist a delta greater than 0 such that 0 less than norm of x minus a less than delta, and we would say that norm of f of x minus b should be less than epsilon, right? This would imply that limit x tends to a, f of x is equals to b, right? Now, this is how we used to define the things. Well, obviously here x belongs to r to the power n, a belongs to r to the power n, while b belongs to r to the power m. Okay. Now, this was how we defined continuity, but for differentiation things would take a little bit of a wide turn. So let us start it. So we want to recall first about our one-dimensional differentiation process. So derivatives in one dimension. So how do we do derivatives in one dimension? We knew that a function f from r to r is differentiable at a belongs to r if there is a number f dash a such that we had limit h tends to 0 f of a plus h minus f of a by h equals to f dash a. So what we used to do is that let me just write down the definition for one dimensional case. Such that limit h tends to 0 f of a plus h minus f of a whole divided by h is equals to f dash t. So this limit, which is denoted by f dash t, is basically called the derivative of f at the point a, and that is how we used to find out derivatives, right? Now, what happens when we switch this definition from this lower dimension to the higher dimensions, where we are no longer concerned with r to r, rather than we are looking at functions from r to the power n to r to the power m? So the heading should be derivatives in higher dimension. Well, now if f is from r to the power n to r to the power m, and let's say there is a point and f is differentiable at a small a belongs to r to the power n, if there exists a linear transformation lambda from r to the power n to r to the power m, such that limit h tends to 0 norm of f of a plus h minus f of a minus lambda of h divided by norm of h equals to 0. And this norm of h is basically this lambda of h is basically that derivative. It's called the derivative. In the one dimensional case, this lambda of h can be defined as follows: lambda of h is f dash a into h. So this is basically the derivative definition for higher dimensions, and we can often say that lambda plus f of a is a good approximation to f of a plus h, or let's say f to f at a. But this is basically the definition that we are going to follow. Now, this linear transformation lambda is called, so lambda of h is called as df of a h, which is the derivative of f at a. Which is the derivative of f at a. So like this is how we are supposed to find out that this things actually work together. Now, a property that I'm going to follow from here on is as follows. Let me just write down the claim or the lemma. So if f from r to the power n to r to the power m is differentiable at some a belongs to r to the power n, and we have this following limit, that is limit h tends to 0, the norm of f of a plus h minus f of a minus lambda of h divided by the norm of h, which is equal to 0, then the linear transformation lambda is unique. So what we want to basically understand here is that for a given function, if it is differentiable and it is differentiable at some point a, then the derivative of it is basically unique. So as you understand from the last section that the linear transformation itself is the derivative of the function, right? So that linear transformation, whatever it is, that must be the derivative of it, and it is unique, so there cannot exist two different derivatives of the same function at the same point. Okay, so how do we prove it? Well, since we already have proved things like this in the past, which is if you want to prove something is unique, so in mathematical terms what you do is you on the contrary assume that that is not unique, and you assume two of them. So you assume two of the different things which have the same property, and then by some way you would like to show that those two things are equal. That is, you want to take two arbitrary linear transformations, let's say lambda and mu, and you would like to say that both of these are derivatives of the function f at the point a, and then somehow you would like to show that basically lambda is equals to mu, which would mean that no matter how many different arbitrary derivatives you might have or you might consider, all of them would be equal, and basically there is only one derivative that exists and is unique. So let us proceed to the proof. Let us assume on the contrary that so we assumed on the contrary that lambda and mu are the two linear transformations that satisfy so they both will satisfy the limiting condition, and the domain and range of them would be r to the power n to r to the power m as well. So let me write it down. So this will be the two conditions that lambda and mu shall satisfy, and you can see a lot of similarities in these two, and something that we can do using these two functions. So how do we proceed from here is something we have seen before when we were doing linear algebra. So what we want to do here is we would like to show that lambda is equals to mu, or rather lambda of h equals to mu of h if we are considering the argument as well. But in general the two linear transformations should be equal. And now how to show that two linear transformations are equal? One way is to consider arbitrary argument x and show that lambda of x equals to mu of x. And to do that, we would first need to understand how to use this to limits, because those are literally the only thing given, apart from the fact that lambda and mu are linear transformations, or basically linear functions. So let us proceed on that. We start with the fact that limit h tends to 0 norm of lambda of h minus mu of h divided by norm of h. Now we would like to evaluate this limit. Now understand that f of a plus h minus f of a is basically a finite it's a finite vector, because it belongs to r to the power m. So let me just erase this part, and what we need to do here is now if we set d of h equals to f of a plus h minus f of a, which also belongs to r to the power m, we can write the limit which we want to calculate as follows. So this can be well written. Now we understand the properties of norm, where we can understand that norm of a plus b is basically less than equals to norm of a plus norm of b, right? So we can write and this is 0 because we know from the given facts that d of h is f of a plus h minus f of a. Now if we name the two conditions 1 and 2, so in one of the conditions it is less than equals to 0, and in another one of the conditions it's greater than equal to 0. It's more like a sandwich theorem. Therefore so this gave us lambda h minus mu h norm divided by h's norm when h tends to 0 is equal to 0. Now this is true for h, right? So this limit goes to 0. Now we can understand that since h is not equals to 0, we must have lambda of h minus mu of h going to 0. Now if h were to be tx, where x not equals to 0 and t tends to 0, we can write, so if h equals to tx where x is not equals to 0 and is arbitrary where t tends to 0, then so t is just a real number here, and this is not a limit where, so here t is just like a real number which is a constant, and x belongs to r to the power n, right? So what happens here is, since lambda and mu are linear operators, we see that since t is a constant, we can write this as t into lambda of x minus t into mu of x divided by t into mod of t into norm of x equals to 0. And this would become mod of t into norm of lambda of x minus mu of x divided by mod of t into norm of x equals to 0. And the mod t is cut off because it's inside the limit and t is not equals to 0 inside the limit. Therefore there is no condition for limit t tends to 0 anymore, and we see that lambda of x minus mu of x, the norm of them, is equals to divided by the norm of x is equals to 0, right? This is for all x belongs to r to the power n. Since x not equals to 0, norm of x would not be equal to 0. Therefore, norm of lambda x minus mu x is equal to 0. And we have known from the properties of norm that if the norm of a function is 0, that function is identically 0, right? So lambda of x minus mu of x is identically equal to 0, which means lambda of x is equals to mu of x, right? So this all correlates the fact that the linear transformation is unique. So observe, we need to show so we want to show that f from r square to r defined by the function f of x comma y equals to square root of modulus of xy is not differentiable at 0 comma 0. Now, well, this is a different type of a problem here, and we are required to show that something is not differentiable rather than differentiable. So what we do here, well, of course some conditions are need to be found, like if you understand that f of x comma 0 is the same as f of 0 comma y, because all of is the same as f of 0 comma 0 and all of them are equal to 0, right? So this means that if we were to find a derivative, we would see, we can see the limit h tends to 0 by mod h, and this should be equals to limit h tends to 0, and since this is already 0, we can write it as 0. Similarly, if we just take the y coordinate, we can still see that this part is again 0. So these two limits turn to 0, and what is disturbing here is that obviously if the derivative were to exist, it has to be 0. But now what we see is that limit f of a plus h b plus k minus f of a comma b so let's say this is the limit we want to find, because if 0 is the unique derivative, then this must be the answer. But now we see that, so we are evaluating at the point 0 comma 0, so it's like f of h comma k, so it's root over modulus of hk. Actually it's root over a plus h into b plus k, so let me just write that down. So 0 plus h into 0 plus k, and minus f of 0 comma 0 is 0 and the derivative is 0, and therefore and the numerator, this one is just h comma k, right? This gives us limit h comma k tends to 0, and this is just root over of modulus of hk divided by root over of h square plus k square. And it is very well known that this limit does not exist, because what we can do here is we can see this limit does not exist, because we can see that for h equals to k we have the sequence limit h comma h to 0 mod h, because that's root over h square, divided by 2 mod h is just equals to 1 by 2, not equals to 0. So this limit is not unique, that means it does not exist, therefore it is not differentiable. Therefore the function f of x comma y equals to root over of mod f x y does not have a derivative at 0 comma 0. So this is what it basically means. Now this is obviously one of the ways we can find out the derivatives, but there are of course other ways we can show that this is not possible. But for instance, let us take a look at another problem. So this is the required function. Just take a good look at it first, and I'll give you like 10 to 15 seconds to think what to do with it. So we basically need to prove that this function is not differentiable at 0 comma 0. So try to find a way to prove that thing. So as you can see that obviously x mod y by root over x square plus y square, and you can see that the difference in the definitions are quite visible, but it still is some basically one of the same definitions that we have used in the above image, because if we were to really find out how to do this problem, then we need to go back to the basics, and we need to go back to the basics of iterated limits, where we learned how to prove that a limit does not exist. So we take different paths along the limits, we play around with the definition of the limit, right? So let us see. First we need to write down the corresponding derivative. So obviously if the derivative were to exist, we would guess that it is 0. This is because limit zero by mod h is equal to 0, and also limit k tends to 0 f of 0 comma k is mod divided by mod of k would also be 0. So this is why we would consider that. Right. So if the derivative were to exist, it would have been 0. Now divided by h comma k. Now this limit should be equal to 0, and that's what we are required to prove, and it should be 0 exactly. If it is not, or if it does not exist, then the derivative does not exist at 0 comma 0. Now and therefore it would seem that the function inside the limit simplifies to the following: h mod k divided by h square plus k squared. And we can see that the limit does not exist by a various methods, but the simplest one is that along the path we have h squared divided by 2h squared, which is basically 1 by 2, and it is not equal to 0. So we can conclude that the limit does not exist and the derivative does not exist, so it's not differentiable at 0 comma 0. So this would be how we would be approaching this problem. Now what we can do is we can do a ton more of problems later on, where we would be doing only problems, the solved problem sections later on. But for now, let us do some basic theorems as well, because they would be required. Now the most important of all is obviously the chain rule. Now we have studied the chain rule in our previous section in one variable calculus, where we were doing the chain rule. Now what we are going to do is we are going to study the chain rule for this multivariable case, which is of utmost importance. So basically, what does it say? So this is how the chain rule works. It's like the same as with the single variable case, but here it says that if f is a function from r to the power n to r to the power m, and it is differentiable at a, so notice that f of a belongs to r to the power m, and we have a function g which goes from r to the power m, so it takes in values from r to the power m and gives in values to r to the power p, and this function g is differentiable at f of a. Okay, because remember that it can be, because f of a is a entry from r to the power m and g has the domain of r to the power m, right? Then the composition g circle f, or g of f basically, which goes from r to the power n to r to the power p, is differentiable at a, and the differentiation is given by this. Well, this can also be written as this in simple terms: g prime of fa, as we used to write in the functions where we had the old chain rule, but this is just a same. Okay, now, well, this is the rule that we are going to follow, and there are other rules that we would also see, but first, some properties about chain rule is very important. In the multidimensional case, we need to understand them carefully. If f from r to the power n to r to the power m is a constant function, okay, is a constant function, that is for some y belongs to r to the power m, we have f of x equals to y for all x belongs to r to the power n. So no matter the input, the output is always y for some y. That is how we called it a constant function. Then d of f at a equals to 0 for all a's. Okay, so the derivative is 0, and it is, as you can see, it's similar for all the functions. It's similar as an analogous to the one variable case. If f from r to the power n to r to the power m is a linear transformation, then d of f at a is basically f. Right? Okay. Number 3. This helps us do the derivatives very easily now, because what we see is this: if f is from r to the power n to r to the power m, so this is the condition that if has like m component functions, which it must have when it gives out a value to m, and this component functions which f had, if all of the fi's are basically differentiable, only and only then we have the whole function differentiable, and the answer is given by df1a, df2a. They can be individually sorted out, right? Now, some of these things would require proof and some of them would not, because the first one seems like a pretty easy thing to do, because we can prove the first one as follows. Since f of x equals to y for all x belongs to r to the power n, and we need to prove the derivative is 0, so let us prove it at an arbitrary point h. Limit h tends to 0, f of a plus h minus f of a minus 0 divided by mod h. So this limit should be 0, and we see that limit h tends to 0. Now f of a plus h is y, so is f of a, because it's a constant function, right? And of course with the norms. So this is basically 0 because the numerator has norm 0. So therefore df of a is basically 0, right? Number 2, so since f is the linear transformation here and we want to prove that the derivative is itself, we can say the following limit f of a plus h minus f of a, and this answer should be f of a into h, right? So this should be the answer that we are looking for, and it shouldn't be f of a into h, it's basically f of h basically. So we can cut this part down, because when you have the function f and the derivative d of f h should be given by f of h. So because that is what we are trying to prove here. But since f is the linear transformation, we see that if you were not clear about this, so there exists a linear transformation lambda h, but we want to prove that the linear transformation is basically the linear transformation that we had before. So starting with the linear transformation, that linear transformation is always differentiable. We have proved that the linear transformation is always differentiable in one of the previous videos. So in this case the answer should be f of h, the derivative should be f of h itself, and we are trying to prove that this limit is 0 so as to establish that fact that the derivative is itself. So we see that since f is a linear transformation, it follows the property of a linear operator. So f of a plus h is basically f of a plus f of h, and we already had minus f of a minus f of h equals to 0 because the numerator is 0. Now, well, this can again be done because we see that this kind of problems can be easily done using all the proper things. Now the proof of number 3 should be something like this. Now we know that we can assume that each fi is differentiable at I. So if each fi at A, and we are claiming that the derivative is this, now what we want to prove is that limit is true. Now we can see that f of a plus h minus f of a minus lambda h is basically equal to, now this whole thing can be found out because it's basically a vector now and f as component function. So we can see that the first component is this minus this minus this, second one is this, and similarly the last one should be this, right? Now therefore limit h tends to 0, f of a plus h minus f of a minus lambda h divided by norm of h, this limit then should be equal to norm of, we know this vector is basically represented as this, and when we take the norm of that, it's basically a summation but in square root form. But we can, since we have already proved that that is less than equals to the mod of that, so what we can find is this is less than equals to summation I equals to 1 to m fi of a plus h minus fi of a minus dfi of a mod of this divided by mod of h. And we do understand that this, all of this limits goes to 0. This is because since fi's are differentiable at a, so because this is true, we know that limit h tends to 0 fi of a plus h minus fi of a minus dfi of a, which is basically the derivative for fi, divided by mod of h equals to 0 for all I belongs to 1 to m. And that is why this is also true, and this proves that the limit is 0, right? So this is another way of doing it. Now if we are given, let's suppose we can turn our attention to a more simplified problem. I hope we can do that. So let's say if and s of x comma y is basically x comma y, then we need to prove that ds of a comma b is basically s itself. It's basically s itself. Now how do we do that? Well, we see that we can directly find out the limit here. Limit h tends to 0, and let us see the norm, because it will be normally a modulus, because you understand that firstly because the output is always a real number, we can have a real number here. So what we have here is as follows. S of a plus h minus comma b plus k minus s of a comma b, and we are calling the linear operator lambda of h comma k, which is basically s itself. Now we want this limit to be 0, or we want to prove that this limit is 0. So let us see how we can do that. Well, s of a plus h comma b plus k is basically equal to, since s of x plus y is defined like that, so a plus b plus h plus k, this is like minus a minus b, and lambda of h comma k, since we want the derivative is itself, it's basically minus h minus k divided by root over of h squared plus k squared. But this is equal to 0 since the numerator is 0, and therefore it is proved that ds of a comma b is simply s. We can find out another one. We can find another one which is as follows. Given that p goes from r squared to r and is defined by p of xy equals to x dot product y, right? Then dp of a comma b x comma y, so derivative of p basically is equals to ay plus bx. So this is what we want to understand here. Thus p prime of a comma b is basically the reverse, which is b comma a, where x and y are basically the coordinates, right? It's basically b comma a. That's what we want to prove. Now we are given that p of x comma y is basically x circle y, so x dot y, right? And we want to prove that like this is true. So this is the linear transformation. So lambda from r squared to r should be is defined as lambda of x comma y bx plus ay. That's how we are going to define it as. And we want the following limit to be 0. So limit h comma k goes to 0 modulus of p of a plus h comma b plus k minus p of a comma b minus lambda of h comma k and this should be equal to 0, or we need to prove it. Now we understand the function and we can write it as limit h comma k goes to 0, and this p of a plus h comma b plus k, this becomes basically a plus h multiplied by b plus k minus p of a comma b is just a cross b. And now lambda of h comma k, this basically is the derivative that we are talking about, and this derivative should be equal to bh plus ak, right? Now limit h comma k to 0. Now if we were to do this, you would find the following: a dot k plus b dot h plus h dot k minus, now bh plus ak is simply is ph b dot h minus a dot k, right? And this is root over of h square plus k square. And now the things cut off, and what we are left with this limit h comma k goes to 0, and modulus of h dot k, which is like the dot product between h and k, that is equal to mod h mod k, and of course the angle between h and k, and this is root over of h square plus k squared, right? Well, this is how it works. And now h and k basically do not really have this, but we can write this as less than equals to limit h comma k goes to 0 mod of hk divided by root over of h square plus k square, right? Now this limit basically can be found out to be 0 because this, since mod of h is less than equals to root over of h square plus k square, and mod of k is less than equals to root over of h square plus k square. Therefore, now the actual limit was this, so I would rather write it as limit hk tends to 0. We need to write it once more. P of a plus h comma b plus k minus p of a comma b minus you had lambda of h comma k divided by h comma k is norm less than equals to actually limit h comma k goes to 0, and what you have here is h square plus k square divided by root over of h square plus k square, but this is equals to limit h comma k goes to 0 root over of h square plus k square, which is undoubtedly 0, and it exists as well. So we find out that this limit is 0, and therefore we can conclude that therefore dp of a comma b for h comma k is lambda h comma k, which is bh plus ak, or in other words p dashed of ab is simply equal to b comma a. And that's how this works. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.